Here we have a nonlinear differential equation that looks like it's a Bernoulli equation, right? So we have y prime, we have y prime, our p of x is -3, our g of x is -1, and then our n is 2. So yeah, this is a Bernoulli equation. So right, the typicals, the only substitution we use is u is equal to y to the 1 minus n. So that's going to be y to the 1 minus 2, so y to the -1. And just going through these steps in case you have to do them on your exam. If we take the derivative then to figure out what y prime is, right, so then we have u prime is going to equal, okay, so a -1 will drop down from the y to the -1. We'll have y to the -2 now, and then another y prime term. If I want to solve for y prime by itself, then that's going to be, let's see, I can move the negative over, I can have the u prime, I can multiply by y squared, and that's it. And that equals y prime. Then I also want to solve, I'm going to need y, so let's just do that in a moment. So right, I have y prime minus 3y equals -y squared. And so here, y prime is -u prime y squared minus 3. I want to get y by itself, and the way I can do that is if I take this equation and I multiply, so I have u equals y to the -1. If I multiply both sides by y squared, I'll get u y squared equals y to the 1. So then I can exchange this y here with uy squared. And then at the end here, I equal -y squared, which is just, we're going to leave that as is. Right, and so then the trick happens where we have y squared in every single term. So we can actually simplify that to -u prime minus 3u equals -1. And now this one doesn't look very terrible to solve. So we can use integrating factor, and why not? That doesn't look too bad. So let's first multiply through by the negative. So we have u prime plus 3u equals 1. So the integrating factor we're going to use is, and this u is still u of t, so our integrating factor, mu of t, is e to the positive 3t, right, because we're doing an indefinite integral of that 3 there, right, that's the e indefinite integral of this piece, so 3 dt, excuse me. That was the 3t. So we multiply that, we get e to the 3t, u prime plus 3 e to the 3t times u equals e to the 3t. All right, and then we can collapse this in a reverse product rule. This is equivalent to e to the 3t times u, the whole thing prime. That still equals e to the 3t. Then we're going to integrate both sides with respect to t. So that will cancel out, the integral and the derivative cancel out. I get e to the 3t times u is equal to, 1/3 e to the 3t plus a constant. And then we can solve for u, so u, and actually let's plug in y now in case it gets a little nasty. So u is actually equal to y to the -1, so then this is the same as e to the 3t, make that t a little more t looking, times 1 over y equals 1/3 e to the 3t plus a constant. All right, well now I've got a fraction, so let's go ahead and try and get rid of all the fractions. Let's multiply everything by 3 and y. Yeah, let's try that. Let's multiply by 3 first. So we'll get 3 e to the 3t over y is equal to, the 3 and the 1/3 cancel, so I have e to the 3t plus 3c, but I can rewrite that as just e to the 3t plus a constant, absorbing the 3 inside. All right, so now I can multiply on this side by y and divide by e to the 3t plus c, so I end up with y equals 3 e to the 3t over e to the 3t plus c. And so that's a solution to this Bernoulli equation. This is actually also the logistic equation, and there are some fixed point solutions, so to worry about those as well. Other solutions are y of t is equal to 0 and y of t is equal to 3. You go back, they do end up satisfying the differential equation. This will work for most initial conditions. But that's solving a Bernoulli equation, and this is what we got, and it was possible to do, and now we're going to do some more.